Welcome back to the OpenFOAM tutorials of the University of Birmingham. This tutorial will show you an example on how to run a simple simulation with OpenFOAM. The example is based on a lid-driven cavity flow. This example will describe how to pre-process, run and post-process a case involving isothermal, incompressible fluid flow in a two-dimensional square domain. A representation of the problem is shown in the figure. The boundaries of the square are walls. The top wall moves in the x direction at a speed of 1 meter per second. The other three walls are stationary. Initially, the flow will be assumed laminar, and will be solved on a uniform mesh using the IcoFoam solver, which has been written for laminar, isothermal, incompressible flow. We will now launch all programs that are required to run a case in OpenFOAM. To access OpenFOAM, we first have to launch Putty. Under Saved Sessions, you can find Bluebear. If you don't have this option, please return back to Tutorial 3, to find instructions on how to configure Putty. Now, I will enter my username and password when prompted. I also have to launch a file transfer program, to transfer files from the Bluebear cluster to my own machine. In this tutorial, I will use WinSCP. In the hostname field, you can see that I have entered bluebear.bham.ac.uk. I have also entered my username. Now I can log in. Enter your own university password. We can see the WinSCP interface. On the left-hand side are documents shown, which are located on my own machine. On the right-hand side, you find the files located on Bluebear. A file can be copied by dragging to the other directory. I have also opened Xseed. This is X Windows Server for access to Linux applications. Before we start, we need to load the OpenFOAM modules in Putty. This needs to be done every time you start using Bluebear. Now the initialization script needs to be sourced as requested. Select the text and use the left mouse button to keep it. Files are required to be placed in specific directories. We will therefore create a folder OpenFOAM in the home directory. With a cd command we enter the seated folder. Now we will create another directory course. Enter the course folder. Create a run folder. Every time the run command will be typed in the command line, it will move us into this directory. We will now go on to solve our first CFD problem. Cases are set up in OpenFOAM by editing case files. A case being simulated involves data from mesh, fields properties, control parameters, amongst other files required to run a simulation. Before I go any further, the case files associated with lid-driven cavity flow can be found in the OpenFOAM tutorials directory. Here, I will copy the cavity case to our home directory, modify the case, and run the simulation. To obtain the files, the following commands are used. Please note the dot at the end of the command line, meaning that the file will be copied in the current directory. This slide shows you the file structure of the case. The case directory is usually given any suitable descriptive name. Here it is called cavity. The system directory is for setting parameters associated with a solution procedure itself. It must contain at least 3 files, the control dict where run control parameters are set, for example the start time, end time, time step and parameters for data output. FV schemes are where discretization schemes are chosen. FV solution is where the equation solver's numerical schemes are chosen and where tolerances for the simulation are set. The constant directory contains a description of the mesh in a subdirectory polymesh and files specifying the physical properties for the application concerned, such as the transport properties, where fluid properties are specified. The time directories contain individual files of data for particular fields. The name of each time directory is based on the simulated time at which the data is written. It is sufficient to say that since we usually start our simulation at time t is 0, the initial conditions are usually stored in a directory named 0. OpenFOAM operates in a three-dimensional Cartesian coordinate system, and all geometries are generated in 3D. OpenFOAM solves any case in 3D by default, but can be instructed to solve in 2D by specifying an empty boundary condition on boundaries normal to the third dimension for which no solution is required. The cavity domain consists of a square of side length d equals 0.1 meter in the xy plane. A uniform mesh of 20 by 20 cells will be used. The block structure is shown in the figure. We first list the contents in the directory. The mesh generator supplied with OpenFOAM is an application block mesh. This application generates meshes from a description specified in an input dictionary file called blockmeshdict, which is located in the constant polymesh directory. Therefore, we will navigate to this directory. We will navigate to the blockmeshdict file. The file can be edited using any text editor. Here we will use gedit. The file starts with header information in the form of a banner. Following this is a foam file subdictionary which is indicated by the text in the curly braces. This contains information about the file. Every file contains a banner and a foam file subdirectory. For simplicity, this information will not be mentioned when looking at all other files. Convert to meters 0.1 implies that the units of the dimensions in the rest of the file are set in 10 cm units. If you wish to use millimeter throughout the file, replace 0.1 with 0.001. Vertices contains a list of all the points that are in the geometry. All vertices contain a x, y and z coordinate. The vertices are numbered in the order they appear, starting from 0. Blocks. The domain can be divided into a number of blocks. In this case we have one block. It starts with the word hex, indicating a hexahedral mesh is specified. Each block contains 8 vertices and these have been labeled from 0 to 7. This indicates that there are 20 cells in the x and y direction and 1 cell in the z direction. The grading is set to simple grading, indicating that the mesh is uniform and no expansion ratios exists. Edges has been left blank, implying all lines between vertices are straight. The line between 2 points can be set to be curved, and is specified in this subdictionary if required. Boundary specifies patches, which are regions in the mesh. The patches are a number of faces grouped together. The patch is given any appropriate name, for example moving wall. The names are used as identifiers for defining boundary conditions. Type refers to the patch type. Here we have walls, and since we are working in 2 dimensions, the faces which are normal to the third dimension, the front and back patch is labeled empty. Faces are the list of block faces which make up the patch. Each block face is defined by a list of 4 vertex numbers. The order in which the vertices are given must be such that, looking from inside the block and starting with any vertex, the vertices which make the face must be traversed in a clockwise direction to define th other vertices. We will now generate the mesh. All applications in OpenFOAM are required to be executed whilst in the case directory. Therefore we are moving back to the case directory now. The mesh is generated by executing the blockmesh.dict file. This is done by running the blockmesh application. The application can be run by typing the following command. OpenFOAM now shows the output generated by running the application. Always check for any errors which may come up. No problems occurred in the application. Now we will check what files have been generated by the blockmesh application. Five files have been generated: boundary, faces, neighbor, owner and points. Collectively these files define the mesh. The mesh should be checked before any solvers are run. To view the mesh, the application foam to Insight should be executed from the case directory. Therefore, we will now navigate back to the case directory. We will now execute the application foam to Insight. A directory named Insight is created. We will now rename the directory to Insight Mesh by the remove command. Information and statistics on the mesh can be obtained by running a mesh checking utility. Any major problems with the mesh will also be highlighted here. The mesh checking utility is called checkmesh. Note that the output would normally be displayed in the command window, but will now be saved to a file called logcheck. We will now view the geometry and mesh. Before we can do this, I need to copy the Insight Mesh directory from the cluster to my own machine by the WinSCP application. In the WinSCP application, the created files are not shown. Regularly refresh the folder to observe changes made in Blue Bear. Now, you can see that our OpenFOAM directory is shown. I will now copy the Insight Mesh directory from the cluster to my computer. This is done by clicking on the right mouse and dragging it to a directory on my own machine. Now, I will launch Insight to open the file. I have opened the copied file. I will now make a clip plane through the domain to view the mesh. The mesh slice will be set in the Z direction. The mesh can now be viewed by clicking on the Display Shaded Surfaces icon. You can now see the mesh. As the mesh looks as expected, Insight can be closed. We will now look into the boundary and initial conditions of the cavity case. From the case directory, I will enter the zero-time directory. The zero-time directory represents the initial fields set up for the case. The directory contains two fields, the pressure field, P, and the velocity field, U. We will first view the contents of the velocity file. Dimensions contains the dimensions of the field. The vector represents meter per second. Each of the 7 scalars represents a power of the SI base unit. In order, the numbers represent mass in kilogram, length in meters, time in seconds, temperature in Kelvin, quantity in kilogram mole, current in amperes, and luminosity intensity expressed in candela. Internal field. The internal velocity field can either be uniform or non-uniform. In this case, initially the whole field is at rest, hence the field is uniform. Boundary field contains information about the boundary condition of the patches. 3 patches were defined in the blockmesh.dict file and each one requires defining. The lid of the container, moving wall, is traveling at 1 meter per second in the x direction. Hence a fixed values is assigned to the patch and the value assigned to it is uniform, 1, 0, 0. The fixed walls do not move in the simulation, hence they are assigned a fixed value of uniform 0. The front and back patch type has been defined as empty. Now we will view the contents of the pressure file. The kinematic pressure has been defined in the dimensions of m² per second squared. The internal field is set to 0, as we are only interested in the relative pressure differences. The wall types are defined as zero gradient, implying the normal gradient if the pressure is 0. Now we will view the physical properties, which are defined in the constants directory. For an icofoam solver, the only property that must be specified is the kinematic viscosity, which is defined in the transport properties file. Initially, this case will be run with a Reynolds number of 10, where the Reynolds number is defined as shown in the formula. Where L is the characteristic length, U the velocity and nu the kinematic viscosity. In this case, L equals 0.1 meter, U, 1 meter per second. So for Reynolds number 10, we choose nu equals 0.01 meters squared per second. In the transport properties file you could see that the aforementioned kinematic viscosity has been defined. Now we will navigate to the system directory. The control DIC contains input data relating to the control of time, and reading and writing of the solution data are read in from this file. The control directory contains information regarding the start time and end times of the simulation. The start time of the simulation has been defined by the keyword start time. The start time has been set to 0 seconds. The stop time of the simulation has been defined by the keyword end time. The end time has been set to 0.5 seconds. To ensure temporal and numerical accuracy, the Coulomb number of the simulation must remain below 1. The Coulomb number is defined as shown in the formula, where delta t is the time step and delta x is the size of the smallest cell in the direction of the velocity. The flow varies everywhere, so to ensure the Coulomb number remains smaller than 1, we choose the worst possible case for delta x. Here, the velocity is 1 meter per second and delta x 0.005 meter, hence delta t must be smaller than or equal to 0.005. Delta t has been set to 0.005. The right control is specified as time step. This implies that the number 20 written in right interval refers to pressure and velocity data fields written into new time directory after of 20 iterations. So this will be at time 0.1, 0.2, 0.3, etc. seconds. The FV schemes file sets the numerical schemes for terms, such as derivatives in equation, that appear in applications being run. We will not be discussing the discretization schemes in details here, but it is worth looking at the file to see how the finite volume methods are applied. All the discretization schemes are set in the directory FV schemes. For this example, the Gaussian finite volume integration is used for the discretization of the divergence terms in the velocity equations. Gaussian integration is based on summing values on cell faces, which must be interpolated from cell centers. The Laplacian terms are discretized using the second-order central difference schemes. The specification of the linear equation solvers and tolerances and other algorithm controls is made in the FV solution file. The first subdictionary in our example is solvers. It specifies each linear solver. The syntax for each entry within solvers uses a keyword that is the word relating to the variable being solved in the particular equation. Here, p and u are being solved for. The solvers are iterative. They are based on reducing the equation residual over a succession of solutions. The residual is a measure of the error in the solution so that the smaller it is, the more accurate the solution. Before solving an equation for a particular field, the initial residual is evaluated based on the current values of the field. After each solver iteration, the residual is re-evaluated. The solver stops if the residual falls below the solver tolerance, or the ratio of the current to initial residuals falls below the solver relative tolerance, rel-tol. The tolerance should represent the level at which the residual is small enough that the solution can be regarded as sufficiently accurate. The solver relative tolerance limits the relative improvement from initial to final solution. In transient simulations, it is usual to set the solver relative tolerance to 0, to force the solution to converge to the solver tolerance in each time step. The second subdirectory is PISO. Most transient fluid dynamics solver applications in OpenFOAM use the pressure implicit split operator, PISO. Algorithms are based on evaluating some initial solutions and correcting them. The user must therefore specify the number of correctors in the PISO dictionary by the nCorrectors keyword. In a close incompressible system, such as the cavity, pressure is relative. It is the pressure difference that matters, not the absolute values. In cases such as this, the solver sets a reference level by pref value in cell pref cell. In this example, both are set to 0. Changing either of these values will change the absolute pressure field, but not the relative pressure or the velocity field. We will now run the simulation. The ICO-foam solver is going to be used. This solver is suitable for transient, incompressible, laminar flow for Newtonian fluids. To run this simulation and save the output to a file called logrun, the following command is entered into the command line. Now, we will look into the logrun directory. First, the details of the simulation are given, such as time, number of processes etc. You could see that the A mesh is created from time step 0 seconds. The output file will show you, for each time step, the mean and maximal Coulomb number. Thank you for watching. In the next tutorial, I will show you how you can post-process the results of this example.